Assalamu alaikum dear students. In previous lecture we discussed the principle of mathematical induction, why to use principle of mathematical induction. Now today we are going to use principle of mathematical induction in these problems. Now the first problem is we have to find the sum of the first n squares, that is 1 square plus 2 square plus so on to. We have to prove that this equals to n into n plus 1 to n plus 1 upon 6. Here given statement is actually to find the sum of the first n squares, and let us suppose that this statement, that's 1 square plus 2 square up to n square, is p of n, because the given statement involves n. That is why we denote this by p of n. Now we will use here the induction because the statement contains the n. That is why we are using the principle of mathematical induction. Now what is principle of mathematical induction? We prove the given statement for the smaller values, that is for n equals to 1. The given statement p of 1 became simply 1 square, because p of n is the sum of the first n squares. So p of 1 is sum of the first 1 squares, that is simply 1 square, which is simply 1. So LHS of this p of n means p of 1 is 1. Now RHS of this is n into n plus 1, 2n plus 1 upon 6. But here n is 1. On substituting n in this, we simply get 1 into 1 plus 1, 2 into 1 plus 1 upon 6, that is simply 2 into 3 upon 6, which is 1. So this means that LHS is RHS, hence for n equals to 1, p of n, that is sum of first square, that is simply 1 square, is n into n plus 1, 2n plus 1 upon 6. Now let us assume that for n equals to k, where k is any positive number or arbitrarily positive number, the given statement is true. That is p of k, which is the sum of the first k squares, 1 square plus 2 square up to k square, is k into k plus 1, 2k plus 1 upon 6. This is assumption. Now we have to prove this statement, that is we will prove the p of n for n equals to k plus 1. Now what is p of k plus 1? P of k plus 1 is the sum of the first k plus 1 squares, that is 1 square, 2 square, k square plus k plus 1 square. Now by assumption, 1 square plus 2 square up to k square is k into k plus 1, 2k plus 1 upon 6, that is this, plus k plus 1 square. Now by cross multiplication, it is k into k plus 1, 2k plus 1 plus 6 into k plus 1 square upon 6. Now taking k plus 1 common, it is 2k square plus k plus 6k plus 1, that is 7k plus 1 here. Now this is the quadratic equation. You can factorize this, and after factorizing, it is simply k plus 1. Now 2 into, actually it is 2 into k plus 2. Now k plus 2 can be written as k plus 1 and plus k plus 2, which is again k plus 1 plus 1. Now here, if for p of n, the statement is n into n plus 1 to n plus 1 upon 6. But here we have to prove the given statement for k plus 1. So RHS should contain first factor as k plus 1, which is k plus 1. Then we have 2 into k plus 1, which is 2 into k plus 1 plus 1, plus n plus 1, that is k plus 1 plus 1, k plus 1 plus 1 upon 6. So this means that the given statement is also true for n equals to k plus 1. Hence by principle of mathematical induction, p of n is true for each and every n. So this means that we can say that sum of the first n squares is n into n plus 1, 2n plus 1 upon 6. Now the problem second is prove that for every positive integer, means we have to prove for all n belongs to natural, 7 raised n minus 3 raised n is divisible by 4. This means that divisible by 4 means 4 divided 7 raised power n minus 3 raised power n. We have to prove this. Now let p of n is 7 raised n minus 3 raised n. That is, the given statement is P of n. We have to prove that 4 divided P of n, that 4 divided 7n minus 3n. Now for n equals to 1. Now when n is 1, P of 1 means given statement is actually 7 1 minus 4, 3 1, which is simply 7 minus 3, that is 4. Now 4 divides 4, so this means that 4 divides P of 1. Hence, this P of n is true for n equals to 1. Now let's assume that the given statement is true for P of k. That is P of k, which is 7k minus 3k. So when it is true by assumption, this means that 4 divides pk. When 4 divides pk, this means that this pk, which is actually 7k minus 3k, is actually 4 into some x, where x is integer. Now we will prove it for n equals to k plus 1. Now P of k plus 1 became a 7k plus 1 minus 3 raised to power k plus 1. Now adding minus 7 3k and subtracting plus 7 3k, that is minus 7 3k and plus 7 into 3k, because this will cancel, we will get this statement, that is 7k plus 1 minus 3k plus 1. Now from this term, take 7 common. It is here, when we take 7 common from 7k plus 1, we are left with 7k minus 3k, and from this take 3k common, it is 7 minus 3. Now 7 minus 3 is 4, and here we have 7 into 7k minus 3k. Here 4 divides 4 means 4 divides 3k into 4. Also 7k minus 3k is divisible by 4, because by assumption given statement is true for n equals to k. So this means that 4 divides the first term, 4 divides the second term. In nutshell, we can say that 4 divides this pk plus 1. So this means that given statement is also true for n equals to k plus 1. Hence 4 divides p of n for all n. Hence by induction, given statement is true. That is 7n minus 3n is divisible by 4. Now the another question is, which is question number 1 of exercise 4.1. 1, we have to prove that 1 plus 3 square up to 3 raised to power n minus 1 is 3 raised to power n minus 1 upon 2. Let P of n be the given statement. Now the given statement is here 1 plus 3 square up to 3 raised to power n minus 1. This is the given statement. Now here 1 is at the first place, 3 is at the second place, 3 square is at third place, and 3 raised to power n minus 1 is at nth place. This means that it contains nth term. So actually this 1 is actually 3 raised to power 1 minus 1, because 1 is at first place. We can write 3 square as 3 raised to power 2 minus 1. We can write this 3 raised power square as 3 minus 2, because 3 square is at the second place, third place. So in this way we can say that nth place of this, or the nth term of this, is 3 raised to power n minus 1. Now for n equals to 1, P of 1 becomes 3 raised to power 1 minus 1, that is 0, which is simply 1, and RHS of this is also 1, because here if we put n equals to 1, 3 raised to power 1 minus 1 upon 2 is 2 upon 2, that is simply 1. So this means that for smaller values, this P of n is true. Now assume that this statement is true for n equals to k. Now P of k becomes 1 plus 3 square plus 3 raised to power k minus 1, because the given statement is Pn, last term is 3 raised to power n minus 1. So here last term becomes, or last term is 3 raised to power k minus 1. Now here we assume that this is true, which implies that this sum is actually 3k minus 1 upon 2. Now we will prove for n equals to k plus 1. Now P of k plus 1 becomes 1 plus 3 square up to 3k minus 1 plus 3k, because in the given statement n contains 3 raised to power n, last term is 3 raised to power n minus 1, while as if we have k plus 1, then the last term becomes 3 raised to power k. But by assumption, 1 plus 3 square up to 3k minus 1 is 3k minus 1 upon 2 plus 3k. Now by cross multiplication it is 3k minus 1 plus 2 into 3k upon 2. Taking 3k common, it is 3k into 1 plus 2 minus 1 upon 2. Now 1 plus 2 is 3. Now 3 into 3k plus 1, when bases are same, powers are added, it is 3 raised to power k plus 1 minus 1 upon 2. Here last term p of n is 3 raised to power n minus 1 upon 2. But here we proved that p of k plus 1 is 3 raised to power k plus 1 minus 1 upon 2. So this means that the given statement is also true for k plus 1. Hence, in nutshell, by induction, we can say that the given statement or this p of n is true for each and every n. That is, p of n is 3 raised to power n minus 1 upon 2 for all n. So inshallah in tomorrow's lecture we will again discuss these questions, that is how to apply the principle of mathematical induction on the given problem. So thank you.